Okay, now we're going to look at the atmosphere. Most people know it's the gas around planet Earth. The question is, where does it end? In terms of life, after 100 kilometers up, there's nothing alive. You'd be long dead. Okay? You're only up a few kilometers in a plane, and already it's fatal for you to be outside there. But we can detect the atmosphere as far as 1,000 kilometers. The Kármán line is what engineers use. They call it 300 kilometers, meaning at about 300 kilometers high, forget about using jets. You've got to switch to rockets. There's just no way. But we're only interested in where life is found. So we're talking the bottom part. The atmosphere is full of mostly nitrogen, which at first seems like it does nothing, but we'll find out later it's really important. 21% oxygen for us and 1% of a few other things. But the part that people forget is there's a lot of water in the air. There's about 13,000 cubic kilometers at any given time. That's 13,000 cubes of water that are 1 kilometer by 1 kilometer by 1 kilometer. So it's basically an entire Lake Superior of humidity in the atmosphere at any given time. Or another way, you took it all out and rained it on Ontario, we would be 13 meters deep in rainwater if we could dry up Earth's atmosphere. That's quite a lot of water vapor in the sky at any time, helping ease up that sunlight a bit. Now let's see the crucial part that people forget about is how the atmosphere is protecting us from being killed by the sun. Here's our spectrum again, from radio waves to gamma rays. The picture just gives you the scale of the size of the waves. Okay? Radio waves, they absolutely get through Earth's atmosphere, which is good, or we wouldn't be talking to people in space. But the Earth's atmosphere does not let microwaves through, which is pretty good, because microwaves are what are in your microwave oven. Those are cooking levels of radiation. And in outer space, the spacecraft have to be hardened against the microwave radiation. If metal gets in your microwave oven, it sparks. So they do have to watch for high levels of microwaves in space. Does infrared and visible get through? Yes, it does, which is great news because that's the light we see and the heat we feel. But after that, when we get into the dangerous spectrum, no. The Earth's atmosphere prevents us from being blasted to non-existence. There would be no life on planet Earth if our atmosphere did not block ultraviolet through gamma rays. Okay? Mars does not have such luck. The worst the UV index gets on planet Earth is 11. On Mars, an average day has a UV index of 50. You would need sunscreen 6 million. There is so much radiation hitting the surface of Mars that if you were there in a spacesuit, it would be like getting a CAT scan once a week. So, and you know, the UV can be shielded on, but the X-rays cannot. So any astronauts who go to Mars are going to be getting like major X-ray doses. The level of radiation is so high reaching the surface of Mars that the soil is actually partially melted and full of horrific compounds called perchlorates that are poisonous to us. So it's farther from the sun, but its lack of atmosphere, Mars is just a radiation death zone as far as humans are concerned. Now let's take a look at how much the Earth's atmosphere protects us from the sun. This is the plot that I showed you earlier of how bright the sunlight is at each wavelength. So the sun is really bright in the yellow-green, and the sun thankfully drops off really fast in the UV. But this outer line with the pale yellow is what the sunlight is like in outer space. The lower line here is what the atmosphere does. So it dims it down quite a bit, but very erratically. Thankfully, look at this gap opening up here. The UV light would have been this bright, but because of the Earth's atmosphere, it was knocked down to this brightness. This level, at about 1300 nanometers, whatever color of light that is beyond our seeing, look what the water vapor did. It took the brightness from here and almost completely knocked out that color. So different gases and vapors in the atmosphere punch holes in the sunlight's brightness and take out quite a bit of the light, even the visible light. The sun is definitely brighter in space than on Earth. But the important part is a lot of the hot rays, the infrared that cook, have been knocked out. And really importantly, the Earth's atmosphere plunges the UV levels on the surface of the Earth. Without that, there would be no life on the planet. Now let's take a look at a graph here that's showing something different and see if we can read the graph. This graph says absorption of light. So the higher it is now is not brightness. This is how much is being sucked up. So the higher the line is, the more the light was absorbed. So let's see if we can read this graph. Does water absorb or transmit the following? So this is what the water vapor in the Earth's atmosphere does. Well, in the ultraviolet band right here that I've highlighted blue, take a look at what's happening. In the UV band, the absorption is really high. So water is absorbing a great deal of the ultraviolet in the Earth's atmosphere coming in from space. So it's not just ozone that gets ultraviolet. Water gets some of it too. Now let's take a look at visible light. Does the water vapor affect visible light at all? Is the visible light being absorbed? Remember, higher up this graph, absorbed. Look at the infrared. Is the infrared...
Mr. Brisson, please call extension 258. Mr. Brisson.
Is the infrared getting absorbed? Far infrared is the heat. Near infrared is what your TV remote controls use. So can you make sense of this graph? If you can, you're seeing graphs that you would do in like grade 11 and 12 physics. Now, what about the light we can't see? Infrared photography is cool. This is a camera that has been adjusted to take pictures in the infrared. And oddly enough, the trees become white and the water becomes black. This is near infrared, it's not thermal. So this is just outside the range of human vision. Dogs, cats, snakes can see into this range. But it is related to the heat. If the object is dark, it's sucking up the light. If it's white, it's kicking it back. This band of light, infrared, is near heat. So you should be able to predict which items are getting warm, which ones are not. So here's again into the further infrared. So this white light, because we can't see infrared, so they just make the camera turn the infrared light to white. This means this tree here is pure white and the grass is pure white, meaning it's throwing the information or the radiation back. Where it's black, the radiation is either being absorbed or going right through it. So here we have absorbed radiation. There is reflective. Now, on a sunny day, does the grass feel cool or hot? The branch of the tree, does it feel cool or hot? Think about it. Now, this is thermal infrared. Thermal infrared is not the light you got from the sun. This is the light your body emits because it's hot. And these cameras are getting really cheap. They were so rare when I was a kid. Now you can buy them at Home Depot. They're still going to set you back $700 or $800, but this is what heat-seeking missiles use. So there's a missile called a Sidewinder missile. It would track heat of an engine, and a Sidewinder snake could see you glowing and follow the heat of your body. And you can see it shows right through the bag because you are the light bulb now. You're not reflecting the light, you are making the thermal infrared. And there are creatures that can see in the thermal infrared. We can do it, but we need special goggles to see that. Now, if we look at skin color under infrared, you can see there are 3 shades of skin color all the same. I have to pause the recording here, and then I'll restart our true colors.